and I'm the Research and Communications Coordinator for the CFRU. For those of you not familiar with the CFRU, we are a stakeholder-driven research cooperative housed at the University of Maine. We have over 30 member organizations, which include forest landowners, wood processors, conservation organizations, and other stakeholders who collectively represent more than 8 million acres of Maine's forests. The CFRU is a core research program in the Center for Research on Sustainable Forests at the University of Maine. This webinar is approved for one Category 1 CFE credit through the Society of American Foresters. If you would like to get credit for this webinar, please fill out the questionnaire that I will be sending you following this webinar as soon as you can. We will take questions at the end of the webinar. At the bottom right of your screen, you should see an online chat box. Feel free to type your questions for the speakers at any time, but I will read through these questions at the end during our Q&A session with our speakers. If you have a question for a specific speaker, please indicate that when you type your question. Today's webinar is on several long-term forest research sites in Maine and how this research has improved our understanding of forest ecology and management in both expected and unexpected ways. I'm excited to introduce our speakers for today's webinar: Ivan Fernandez, Professor of Soil Science in the School of Forest Resources and the Climate Change Institute at the University of Maine, and Brian Roth, the program leader here at the CFRU. We will start now with Ivan's presentation on research conducted at the Brook Watershed in Maine. And so without further ado, I'll turn it over to Ivan.
Thank you, Jenna. Pleased to be able to talk about the Brook project this afternoon. And while Jenna's getting the slides going, got a backup one.
Could you press the back arrow on the keyboard? Yep.
There we go. Lost my train of thought already. Pleasure to be able to talk about the Brook project this afternoon, and I have some sense of what the audience is. And my goal here is not to get wonkish about the details of the project. I'm a soil scientist and study a lot of things from a sort of biogeochemical standpoint. But I think the message here is the value of long-term research, and we have a number of different study sites in different arenas throughout Maine. I've been directly involved with a number of them over my career, and Brook certainly being one of them. And so what I wanted to do over the next 30 minutes is to tell you about the Brook project and some of the things that we've learned, but even more importantly, how long-term research projects can be valuable in ways that are both expected and unexpected. So without further ado, let's see if this works. Yeah. So where did the project start? It started back in the 1980s, and at the time we were, as a nation, interested in understanding the risks of air pollution, and particularly acid rain, sulfur and nitrogen deposition. There was a congressionally mandated timeline that led to evaluating the Clean Air Act in 1990. And so between 1980 and 1990, the U.S. had a program called the National Acid Precipitation Assessment Program, NAPAP. Which was a program of research designed to inform Congress about the decisions it would make on the Clean Air Act in 1990. And many of you know that our own Senator Mitchell was a key figure in those discussions and led that effort. It was managed by the Interagency Task Force on Climate Change, which was, I think, one of those good examples of agencies working together for a common cause and managing those resources, I think, very appropriately. And I think they did a great job. And so it was during that period of time, the big question was, how much should we regulate sulfur and nitrogen emissions from smokestacks, particularly, and particularly sulfur, in order to protect resources in the future. And by the middle of the 1980s, the focus really was on surface waters, lakes and streams, and forests. And the goal was to try and figure out what science needed to be done in order to answer the question of how much regulation should be developed or employed through or deployed through the Clean Air Act Too much is spending money or will have costs that are unwarranted, and too little won't protect resources, natural resources of the future. So kind of a big challenge, and we face this often in environmental policy. And so what do you do in order to address that? In other words, how do you study the future? And there's kind of three ways to do it. One is you measure it, meaning long-term monitoring you might think of, and I never think of, although there's been times when monitoring takes on a sort of dirty word connotation because it's expensive and it kind of goes on, and people rightfully ask, why is this valuable? Most of the time there's lots of evidence of the value of long-term monitoring, but it takes time. And so you can't wait for 100 years to see what the consequences of regulations might be, because you've got to make the decisions today. And so long-term monitoring is a part of it, but it usually doesn't answer the short-term questions. Another approach is to substitute space for time. And so where there's a stressor in the environment that you can identify a spatial gradient, you can essentially lay out plots or do studies across that gradient. And we've done those kinds of studies. We've done them in Maine for climate, for heavy metals in the environment, and some for acid rain. There's artifacts and drawbacks with each one of these kinds of approaches. The third, and the most sort of compelling on one hand, and on the other hand fraught with concerns about artifacts, rightfully so, are experimental manipulations. And so can we alter the ecosystem in ways that might inform us about how ecosystems change over the long haul? And all of these have their value, and particularly when you work together with studies in all these categories, it becomes the most powerful way to address the science. The science from all of those feeds into models, and models are the most sort of robust approach to answer lots of different questions about different scenarios today and in the future, and hindcast into the past. I like models a lot, but I also want to often point out that models are all wrong. Lots of them are pretty good and lots of them are useful, but they're all imperfect in regards to the ability to absolutely predict what the future will be. Really, only long-term monitoring gets us there. So Bear Brook was born from item number 3 here, to simulate the future. And in the middle of the 1980s, EPA was charged with developing science that would inform Congress for the Clean Air Act. There were 3 computer models, ILWAS, Trickle Down, and MAGIC, that were primarily used in order to answer questions for Congress as to the consequences, the benefits of different levels of sulfur and nitrogen regulation. As some of you may know, the Clean Air Act reauthorization of 1990 focused primarily on sulfur, did a great job on that, and less so on nitrogen. And today we have significantly less sulfur deposition, about 70% here, and about half the nitrogen deposition over time. This research was funded by a number of different sources. At the beginning, it was all EPA. And for the last 15 to 20 years, it's been dominated by the National Science Foundation. The folks at American Forest Management have been partners throughout the entire life of the project. Landowners have changed over time, but and USGS was a partner in gauging the streams for a long time, till basically we didn't have the funding to share the contract with them, and so we do the gauging ourselves. So the Bear Brook Watershed is in down east Maine, near Beddington, off Route 9, for those that are familiar with the area. It's on Lead Mountain, but we don't say Lead Mountain because in a geologic world, people might say, is there lead sulfide in the bedrock? And there's not. But that would be a problem for our experiment. We checked before we started. So we call it the Bear Brook Watershed, Maine. There's 2 catchments paired side by side, about 10 hectares, a little over 10 hectares each, laid out on the side of the mountain. The East Bear Brook watershed is our reference watershed. We've not treated that during for the most part. We haven't treated that during the years of research. And the West Bear is the treated watershed. And if you've got sharp eyes, or for those that are listening that know the site, you can see the little two divots down here at the bottom, which is where the weirs are. Those allow us to gauge the stream export hydrologically, and we measure what's in it chemically. And then the various devices, these are aerometric rain gauges and a Belfort rain gauge, allow us to measure the precipitation coming in. And so each one of these units, they were assessed for relatively tight bedrock. So each one of these units is at least hydrologically relatively secure in that we're not leaking anything down through the bedrock. What falls on that piece of landscape all drains, at least in the liquid form, drains through that V-notch weir. So the experiment was basically to simulate higher levels of acid deposition and address questions of ecosystem response and whether the models could predict it accurately. We began treatments of the West Bear watershed in November of 1989, and we flew helicopters in order to apply the treatments. I say we, I've never flown the helicopter, but we had really competent people that flew the helicopter. The treatment was 1,800 equivalents per hectare per year. That's kind of a wonky form of it, which it was the same as 25 and 28 kilograms per hectare per year of nitrogen and sulfur. At the time, that was not outrageously high values in considering some of the areas in the eastern United States, like the Smokies, that were receiving relatively high levels of air pollution inputs into the landscape. And of course, we've always been on the low end of the scale because we're farther down the pipeline, and that's one of the reasons that they first came to Maine to talk to us about doing this, this research. Treatments are applied bi-monthly, and they have been for 27 years. We'll just touch on the recovery part today, but West Bear recovery experiment began in October 2016, where we stopped treating. And so now we're in West Bear looking at experimental recovery. And of course, in East Bear, in the reference watershed, we've been studying the response to the Clean Air Act over the last 3 decades. So the framework for this is a watershed. The value of a watershed is it's kind of a black box. You measure what goes in, you measure what comes out, and you're able to evaluate what's accumulating and what's being depleted. That's a close-up of the same equipment that we looked at in that other slide. That's cool. Gives us a lot of information, but it's really what goes on inside the box that's the most interesting and where we've spent most of our time. If we think of a raindrop traversing through the ecosystem, we've done studies over the last 30 years of all sorts of different components of the watershed, usually based on student and projects, undergraduate and graduate student projects, and individual contracts. This is not a national forest or a publicly owned land, as I've already pointed out. We're there in partnership with American Forest Management, and we go from grant to grant to keep the project running, and we have for 3 decades at this point in time. So many of those items on the list and other things that we've done, we do for periods of time. The few things that have been consistent over the entire time period have been the mass balance using precipitation and stream flow, which has been the most intense and ongoing to today long-term data set. So what are the values of doing this? Well, the first obvious reason that we did it was to test models. And I already mentioned that there were 3 at the time. So in the late 1980s, 3 models that were being used to answer the question, what if we reduce emissions by X amount? Problem was all of those models were developed for certain specific sites or areas. And the Bear Brook project was established as part of a set of studies to try to determine how robust and accurate those models were. So this is the kind of data we look at a lot, and we have a lot of. These are stream chemistry data, and the parameter that this slide shows is sulfate. This vertical line here is the marks on the calendar when we began the treatment, so that's November of 1989. The dark circles are East Bear, our reference watershed, which is not being treated. And the open circles is West Bear. We studied, measured the streams. We did plot work outside of the watershed for the first several years and monitored these streams in order to determine how comparable they were. Because if we wanted to use one as a reference and manipulate the other, we needed them to behave similarly. And we had surveyed over 70 sites throughout the state prior to deciding on this location. So we were pretty sure we had picked a good site, but we needed to demonstrate that. And as you see, the sulfate concentrations were very comparable in the two streams over the first couple of years before treatments began. As soon as we began to treat with ammonium sulfate, to no one's surprise, sulfate concentrations increased. And so this is allowing us to understand and begin to study the way soils and the ecosystem processes sulfate. And it continued to increase for about a decade. In fact, the one model we used the most at this site was MAGIC of the three, which is an acronym, not real magic. And the model predicted that the increase would take place, and it was very good for the first decade, but it wasn't quite as good for the second decade. And so it was supposed to sort of level out at 300 microequivalents per liter or thereabouts, and it leveled out at about 200 microequivalents. And so instead of being way up here where the model predicted it would be, it was down here, which is sort of lesson one in the discussion this afternoon about the need to do long-term research if you're trying to understand long-term processes and ecosystem behavior. And so for the first decade, you were fine, but if you were using those models, as we were, in order to predict 30, 40, 50, and a century later, they probably needed to be improved. We also would notice that here is a good example of the value of monitoring. You see that sulfate concentrations in East Bear is going down, and this is the ambient recovery experiment, because this is the response to improvements from the Clean Air Act and declining sulfur deposition over the last 3 decades. This decline is not as steep as the actual decline in the deposition, which has to do with the way the ecosystem stores sulfate and buffers both response and particularly recovery. Another example of a model is the conceptual model from Galloway and others in the early 1980s that described stream acidification processes. It's simpler than it looks. It looks a little more complicated here. This is a conceptual model figure that's representing increases plus BC or decreases minus BC in the base cation concentrations in the stream. So that would be calcium, magnesium, potassium concentrations in the streams. And if the streams get acidified, then you lose base cations. And if the streams are alkalized, it would be an increase in base cations. And phase 1 here is before the treatment, and phase 2 is conceptually we turn on acid rain. And this arrow represents the period of time when acid rain is being applied, and then you go into phase 5 here, and you would turn it off. And we're not going to focus on the recovery right now. And so what did we expect to happen? We expected that as streams began to be acidified, base cations from the soils would be exported, increasingly so, and that we would see an increase in concentrations in the base cations in the streams. Meanwhile, the base saturation in the soil, and that's what the solid line is, would be declining. The base saturation in the soil would continue to decline until it reached some new lower acidified level. Stream concentrations of base cations would increase, kind of turn a corner when you got to a certain base saturation, and then begin to decline. And this is the fundamentals of acidification and base cation loss that underpin all of the models in relative to acidification processes. So what did our watershed do? Focus on the big colorful arrows here. This is a plot of concentrations in the stream of both calcium and magnesium. So there's magnesium, there's calcium. Here it's a little different because they're plotted against each other. But suffice it to say that if we go in this direction, concentrations of both are increasing. And if we go in this direction, concentrations of both are decreasing. And each one of these circles is the average concentration of both for a given year. And all of those numbers are the last two numbers of the different years up to about 2012 in this plot. Otherwise, it really gets noisy. In here, you have to trust me, you don't need to track them down real fast, is where we started, and both East and West Bear were comparable. And as we began to treat the watershed, West Bear, the treated watershed, had increasing concentrations. East Bear, the reference watershed, since we began the experiment, has had continuously declining concentrations of base cations. Around 1995, the concentration of base cations turned the corner. And if we go back to our conceptual model, we're basically representing this transition from increasing to decreasing base cations, and that's exactly what we saw in the watersheds. And after that period of time, and ever since, the base cations have been declining, similar to East Bear. However, there's higher sulfate concentrations in the West Bear streams from the treatments, and so the concentrations are elevated. So here we saw over several decades, essentially the validation of a conceptual model which frames a numerical model that underpins these models that were predicting acidification response. One of the other advantages of doing long-term research is that you learn a lot of stuff you didn't plan on learning along the way. And lots of times we learn even more than that. And we'll often say that we know now the questions to ask. We didn't even know the right questions to ask, really, about ecosystem function when we started the experiment. And so this I call ecological surprises and stochasticity, stuff that just happens. And if you're there and you've measured ecosystem processes over time, you understand temporal and spatial variability, then you can put in context the importance of those responses. I'm going to use nitrogen as an example or a couple of examples from the nitrogen story at Bear Brook to give sort of some examples of what I mean by that, those concepts. This is a little less noisy time series. This is actually draft data. It's not volume weighted yet, but it tells the story. This is nitrate in stream water. And the dark circle, the filled in circles here are West Bear, the treated watershed, and the open circles are East Bear, the reference watershed. Just like with sulfate, this is when the treatments began. Remember, we're adding ammonium sulfate, so the treatment is NH4, ammonium. They behaved very similarly before the treatments began. We began to treat in fall of 1989. I will say that you see that concentrations in both watersheds, the streams for both watersheds were elevated, and they were throughout the Northeast at that point in time. And at the time, we were all running around thinking, maybe nitrogen saturation is now emerging, and we've reached a threshold. And it wasn't. It was a short-term weather impact, a climatic impact of cold winters that caused a certain kind of freezing that made the systems leaky for a few years, and then it went back to baseline. And so this is zero, and so these concentrations in most of these streams are really, really low. For the treatment, however, we saw an immediate response in stream nitrate concentrations. A little bit interesting because we were adding ammonium, there's the NH4, and almost overnight what we started to see was excess nitrate coming out in the streams. And so we could hypothesize that the ammonia must have been nitrified faster than we anticipated in order to produce that nitrate that we were seeing in the streams. What we learned was that this initial nitrate for the first couple of years that was coming out actually wasn't the nitrogen we were adding. It's nitrogen that was in the soil, and the ammonium addition suppressed some of the mechanisms in the soil that utilized the nitrate, microbial utilization primarily, and some root uptake. So that the sink for nitrate was impeded by the ammonium, and therefore native nitrogen in the form of nitrate started to leak immediately. 2 years later, as a result of some isotopic studies that we did, we learned that, so it took a couple of years before we started to see the new nitrogen that we were adding show up in the stream nitrate, which gave us insight on the mechanisms both of the native pools as well as what was happening to the treatment that we were adding. A little later, in the category of stochastic events, many of us remember the 1998 ice storm. We had relatively minor small areas of the watershed that were impacted in canopy from that storm, but it was enough of a disturbance that we saw a clear and multi-year response in nitrate export as a result of that perturbation, which is not surprising. We perturbed the forest ecosystem, nutrients come pouring out. We didn't think we would see it with the relatively small amount of damage that occurred, but we did, and it lasted for a couple of years. Moving forward, we recently just wrapped up a study of summarizing some of the growth data in the forest, and by having the long-term record of behavior and intensive measurements of forest growth at that point, we were able to demonstrate that about 24% of or there was about a 24% increase in the amount of nitrogen standing in the forest above ground in West Bear, the treated watershed, and pretty close to that increased biomass accumulation as compared to the East Bear reference watershed. So we weren't damaging trees with our treatment. We were increasing their growth rate. During that period of time, we've also seen changes in temperatures and CO2 concentrations, et cetera, that would influence both watersheds. And very recently, we've seen in the literature, and we see it in our own data, discussions of oligotrophication of the landscape of surface waters and forests, meaning that the pollutant deposition has decreased by about 50%. And that's an essential nutrient, and it's limiting in our forests. And so now we're seeing, instead of eutrophication, sort of the opposite. And it could potentially having interesting impacts on ecosystem function. This is the dashed line marking when we turned off the treatments. And so the last thing we see here is we're able to look at recovery, just like the response. Nitrate recovered essentially overnight. And even though almost 80% of the excess nitrogen that we've put on the watershed in the 27 years of treatments is still in the watershed, very little is leaking out, and that response happened almost immediately. And so now we're actively engaged in tracking it in the ecosystem and seeing how it is changing function. So switching from some of the nitty-gritty of data, I think there's a number of things that are valuable from long-term research. We find that when we do certain things for other purposes, we go and look for where is a good place to get good data. And Bear Brook, we're fortunately, we've been there for a long time. We've spent about $14 million on that site. And so we have a lot of data that could be used for other purposes. It may be the most data intensive relative to biogeochemistry in the state. And for an example, a few years ago, a graduate student was doing some modeling of the impacts of different thinning treatments on biomass accumulation and nutrient accumulation with an eye towards nutrient depletion concerns. Her modeling was on using for balsam fir using 3 different site index classes. The details here are not the point. It's mostly eye candy to make the point that when we went to do this, of course, in our case, it was in my own program, so we were able to go to the Bear Brook data for foliar concentrations and soil concentrations and do a great job parameterizing the model in order to ask a question that is very different than what the original experiment was designed to do. And we've contributed data to many different efforts in this kind of context. Bear Brook's been valuable in what we might call the regionalization of science, one case study at a time. So these things are really expensive, and yet there's a lot of different study groups and organizations doing intensive forest ecosystem research. And it becomes very powerful when you can pool your data across these study sites. When you're by yourself, you're a case study, so you're not really sure how the rest of the world behaves, although we obviously can make some inferences. When you've got 20 or 30 sites of this scale across a landscape, and you can ask different kinds of questions, and the results are very robust. We've been involved in a lot of these, and we've been fortunate to be a partner with a number of different sites. So this is the front page, basically, of a paper a couple of years ago led by Greg Lawrence with the U.S. Geologic Survey in New York, and a number of us from throughout the northeastern U.S. and eastern Canada that had long-term study sites and looked at potential evidence for recovery in soils. Recovery from declining sulfur deposition. There's a fair body of literature that shows evidence of recovery, partial recovery in all these cases, but not total recovery, but in surface waters, but the rest of the ecosystems are kind of more complex. Well, this is probably the first study to demonstrate evidence in soils of recovery from acid deposition, and Bear Brook was one of a number of different sites. Bear Brook was also highlighted in this paper because of our experimental treatment. We were able to essentially experimentally support the hypothesis that was being presented across all of the sites in this paper. And studies like this are, of course, important for informing policy. In this case, that's the reason this one got started. The most important aspect of where this science has been used is in the Clean Air Act. The congressionally authorized Clean Air Science Advisory Committee for the Environmental Protection Agency has the responsibility to evaluate the Clean Air Act, both primary and secondary effects. Secondary effects are ecological effects. Primary effects are human health effects. And they're currently undergoing the evaluation of the National Ambient Air Quality Standards for oxides of both sulfur and nitrogen. That image on the right is the multi-year process every cycle that this takes place. And it's happened a number of times since 1990. The big science part of it is the integrated science assessment. That document was 1,800 pages in draft form last summer. And Bear Brook science and references are one of obviously many, but that contribute to that science that underpins the development of policy. There are actually 6 sites that were used in that as case studies from the United States, and Bear Brook, we're fortunate to be one of them. So we feel pretty good about the original establishment of Bear Brook in the middle of the 1980s to inform 1990. There was some of our science that was included in that, but that was like 3 years. So pretty hard to be too useful in a short period of time. 30 years later, we have a lot to contribute and have in many ways. So concluding comments here is long-term research is a favorite topic of mine, and I think really important. It's more critical now in a period of accelerating change than ever before. It really is essential for cost-effective environmental policy. Clean Air Act paid us back about 30 to 1 for the investment in sulfur regulations, and we're demonstrating the changes in the ecosystems. It's essential for cost-effective natural resource management. And if we're doing this kind of long-term research, we can document both our successes and failures, and each are equally important. So conclude by saying time is on our side.
Great. Well, thank you, Ivan. Thanks for that presentation. And next up, we have Brian Roth, who will be speaking on several long-term forest research studies here in Maine that have been managed by the CFRU.
Well, good afternoon. This is Brian Roth with the CFRU. I'm really excited to be here to present this webinar on long-term research in forestry, and hope you're enjoying this webinar series that we've started. Jen has done a great job in hosting these webinars and organizing the speakers, and we're going to continue. So first, I'd like to thank Dr. Fernandez for an excellent talk on his and all his contributions to forest ecosystem research over the years. Really exciting to see this, and it reminds me how this long-term research will often last longer than the careers of the scientists that put them in. So we're really, just like foresters, you know, what we're doing now, it's others later on that will either reap the rewards or pay a price for what we've done. So with that, let's move on. All right, so for over 40 years, we've been doing stakeholder-driven research. A long team history before me was starting with Fred Knight at the college, and Max McCormick and Bob Seymour and Mark Hauswehr as scientists. Later with Bob Wagner, moving the program forward from the 90s till when I arrived here about 8 years ago as an associate director and now a program leader. So very humbled at this past and excited about the things that we're doing now and how we're moving forward with things. So a little overview of the talk today. Going to start out with a couple of our long-term trials. Austin Pond is the longest serving trial in the CFRU. Weymouth Point not much further behind. A new one as we move forward and look to the future, Maine's Adaptive Silviculture Network, which is just getting going, and we'll talk a little bit about it at the end and what the future is going to build. Of course, a lot of people to acknowledge, too many to even put on here, but I made an effort, so it's really important to acknowledge all of the work that's been done in the past, and everything kind of builds, and we build on top of what others have done before us. So I thought I'd start out with kind of what I think makes a valuable long-term forest research study. Ivan mentioned several of them, and so I won't repeat those, but one of the things that's important is to really get some replication across the landscape. That increases the scope and the value of the trials. The Austin Pond and Weymouth Point are just single locations. I wish we had them all across the landscape. That would be exciting and expensive. Large treatment areas are very useful, and we'll see why that's important as we talk about these different trials today. And just to have something that's operational, but really to push the boundaries, stretch those out, things that we may not think about doing today, but may in the future. We think about a carbon market. Maybe we're going to be growing carbon in the future, and that's something that would involve a different silvicultural treatment. We would like to have representative stand types and something that's so exciting, it's going to attract a big, broad, diverse team of researchers from around the region. And that's going to attract multiple funding, and we're going to be successful. You've seen what Ivan was able to do at Bear Brook. Just amazing how he's able to chase money from different sources, and the flavor changes as we go along, but it all starts with this really good field experiment on the ground, a network that's going to have long-term value and hopefully will last for multiple generations. So the oldest trial, this is the Austin Pond study. This was established in 1977 by Max McCormick. This is actually the oldest active vegetation management trial in the Northeast. It has a nice reputation for that. This is a picture from 1989 that Steve Coleman, the late Steve Coleman, took from the airplane. I think Max was up there with him. The history at Austin Pond, there's a long list here. And it kind of goes along with what Ivan was explaining, that we put in these trials with one intention, and then if we are lucky, we're going to get a bunch more values and benefits as we go forward, answering questions we may not have even known that we were going to be able to answer. So starting in 1970, that site was a clear cut. This is following the spruce budworm outbreak. Herbicide study was installed. That was really a screening trial. Max had no intention of this thing running that long. I know he scolds me often, but it really was well done. They got the answers they needed, but we kept it going because by 1986, there was an interest in not only controlling vegetation to promote softwood, but these dense stands of softwood needed to be thinned. And so we had a perfect platform to test some pre-commercial thinning. So half of those of each plot was thinned. Later, we did some biomass and growth response. That's with Ron Lemin and Max McCormick. And then some permanent sample plots put in later with Howard Daggett on his master's work. They were able to look at overstory and understory. By age 40, John Brissett and Bob Wagner and they were able to, and Matt Olson were able to look at 40 years of development of these stands, because now you have stands going in different directions from common starting point, and that was very interesting. And right about when I got here, there was an interest in doing commercial thinning. The stands had matured to the point where there was an opportunity to maybe put this thing all the way to rotation length, which would need a commercial thinning. So we installed a bunch of commercial thinning and learned a bunch of things from that. And so we'll talk about those things as we move on here. So again, it was established in 1977. Here's a little picture. These are about a little over 2 acres in size, and you can see the labels, what was on there. All of those treatments worked. Here's 5 years after the herbicide treatment. This is my mentor, Dr. Mike Newton from Oregon State University. I did a master's degree in herbicide work with Mike back in the early 90s, and he was always talking about Maine and this Austin Pond trial. Just amazing to see the response when you control the competing vegetation and hardwoods, how quickly our conifers will respond. You can see on the left is the spruce and the right is the fir. Well, that led us then to look at pre-commercial thinning, and you can see how, because the plots that Max put in, he put them in with a helicopter, they were big enough that we were able to actually split that. And again, I say we, I wasn't here, but we take advantage of these things. 1986, they put a strip down the middle and treated half of each plot and was able to get a 2 by 2 factorial in a way. And here's what the results from that would look like. This is 16 years following the herbicide, 23 years after it was clear cut, so 7 years then on the PCT. That cookie is something that Max shows me every time, how quickly the trees respond to space, that the trees are too close together in Maine. That graph on the y-axis here, this is the merchantable softwood volume. So these are trees that are big enough to harvest. On the y-axis, on the x-axis is the softwood importance, so how dominated by softwoods they are. So you can see 2 groups here that have a circle around them. The herbicide treatments, all of them worked. They all increased the presence of softwood, and the PCT increased the amount of merchantable softwood. So nothing extraordinary that we couldn't have figured out without the trial, but at least now we have some data from a controlled experiment that we can make models and predict economics and predict what we would do in the future. So I mentioned the third wave of treatments. This is the commercial thinning, and this was again just to provide some more data and drive these stands further along their development and try to get rotation lengths. You can see that we had PCT treatments and no PCT treatments, and then a range of management objectives, including a start over clear cut, which is sometimes what needs to happen in an overstocked softwood stand in northern Maine. There's a map of all of the different treatments. Those are about 1 acre in size. There's some replication there. And it's just to give you an idea of how big some of these experiments are and the management implications to looking after those. Here's a pretty picture of the commercial thinning that we did while we were out there. This is in a heavy thinning. in a spruce dominated stand at Austin Pond. So Patrick Hiesel, he's an assistant professor now at Clemson University. Here he did his master's and PhD work on this project, and he was able to show that it's really you need to match the harvest system to the stand conditions. So the cut to length system is best in PCT stands, and the non-PCT stands was whole tree harvest. Again, not surprising, but he was able to quantify those costs on productivity across the different levels of removals. At the same time, we had Cody LaChance do his master's degree here. Cody is now a forester with SAPI. He was looking at stem damage, residual stem damage. We thought this would be a good opportunity to study what's there now and then follow it through to the end of the rotation as far as what is the effect on growth and wood quality. So initially, he showed how there is more damage closer to the trails as one would expect. That's the y-axis on this graph. As you go from the edge of the trail towards the middle of the trail, and this is a probability of wounding. Each curve represents a different density of thinning or harvest removal, whether it's in the PCT or no PCT. So stands that were overstocked to start with had the most damage, and that was evident when you removed half of the basal area. Okay, moving on, Weymouth Point study. This is another paired watershed study. This one, we're looking at Spruce-Fir productivity with harvest removals, nutrient removals of residues. It's one of three in Maine. This one is started out as a Forest Service regional study. These regional studies are quite exciting. This one, it happened to be the only Spruce-Fir installation up there in Maine in T4R12. The others are in Vermont, New Hampshire, Connecticut, and they're in hardwoods. You can see the stars on the map. This one was initiated in 1979, again, Max McCormick with his graduate student Tat Smith working on his PhD, looking at whole tree harvesting and nutrient retention. And I thought this was interesting. Ivan, this is only one of three paired watershed trials in Maine, with Brook being the other. Here's the history. Initiated that study in '79 with 2 years of monitoring, looking at soil solution and stream water chemistry. 1981, one of those catchments, one of the watersheds was harvested, a whole tree harvest. By 1985, it had a release treatment that was treated with triclopyr, which is a forest herbicide. Gave an opportunity to study the triclopyr residue that's in the soils and flowing out of the system because they're doing stream monitoring. Later on, Russ Briggs, a scientist with the CFRU for the early 90s, he's now at SUNY ESF. He put in 27 plots all across those drainage classes and added a layer of follow-up treatment with pre-commercial thinning, like at Austin Pond, but also fertilization. So this was kind of a factorial experiment. Later, Richard Cobb, who did his degree here, his undergraduate or a graduate degree, put in some more PCT plots, looking at similar things with Jim McLaughlin, soil nutrients and carbon in those plots. And finally, we've been back to remonument the stands for the next round. This is a mid-rotation. We're at about 35 years when we started this study. And this is Tat Smith and another dream team of scientists, including Ivan Fernandez and others, looking at what are the midterm effects of whole tree harvesting on productivity, nutrients, and carbon. So quite exciting. Here's a picture from the time of harvest. Those of you will recognize those machines. Those are coring feller forwarders. There's two of them in case one of them gets stuck. Apparently they're very big. There's the design. So this part here was the treated half, and this is the non-treated half, and you can see the plots that are out there and then an air photo. Just a little background on the actual treatments. The harvesting and delimbing residues, then in 1981, there was a whole tree harvesting. So that's kind of the business as usual. And then there were plots where the branches and tops were put back onto that plot that had been removed. So you could see what would be the effect of a stem only harvest. And then what would happen if those residues were chipped and distributed evenly? There's some of the harvest pictures, just kind of moving through. Here's the watershed, the soil solution with the lysimeters and sampling. You can see TAT organizing the lysimeters to put in the ground and the wells. They developed biomass equations. They looked at nutrient contents. There's Pat Strout, who was their chainsaw guy at the time, and Tat Smith. And then finally, redistributing the harvest slash and the chipping. This is a picture of Wayne Martin, who is at Hubbard Brook. He had the foresight to put in a bunch of transects because he was concerned about the effect of the soil disturbance at the time. And that's what we see here. This isn't at Austin Pond, but it's nearby, or at Weymouth Point. We were able to take advantage of these by, because these were so well monumented, and Wayne had the data. When I called him, he went to his attic and he got it for me. We were able to remonument these and actually look years later, 35 years later, what is the effect of these severe ruts? And you can see a picture here from a couple years ago that there's some still around. We were curious about how does this influence the growth of the crop trees that are surrounding these in proximity. And this was some of the work that Cody LeChance had done. So he took some stem cores and looked at the growth of those trees over time. So this would be the outside of the tree moving towards the inside. And this is how much each ring grew. And you could see that trees that had high disturbance, the ones closest to the ruts, had a lot of, there was no difference between them. And the variation here is due to climate. So that was an interesting result. Right now, we have ongoing research on soils, a lot of soils work going on with Tat Smith and a series of graduate students looking at the residues on the forest floor across the different treatments. Things have decomposed across the entire study. Same thing with total carbon, looking in the soils, not much difference between treatments. So same thing on nitrogen, maybe a slight increase, but nothing significant. So moving on, what do we want to do for the future, knowing that there are some limitations to these studies? Well, this is where we came up with the Adaptive Silviculture Network. So this is the next generation, a place where we can demonstrate a wide variety of silviculture options, quantify productivity, look at some growth and yield modeling, getting data from remote sensing, a lot of things that we don't know that we will have answers to. We can go to this place and do that, including wildlife management. There's going to be at least 18 installations. We want to cover all of the stand types and also site qualities within those and spread this out around the state. We always start with a uniform starting condition so that there's a level playing field. This happens to be a Weyerhaeuser site up in Thorndike Township, that these are going to be the treatment areas, and then we'd randomize what gets done in each of those. Just a whole list of silvicultural treatments from clear cuts to partial harvest. It's kind of the good, the bad, the ugly, things that representative of Maine right now, and it can vary, but there's kind of a core series of treatments that go through them. Here's a picture from the J.D. Irving site, just for eye candy. There's the AFM site, those foresters that are watching this presentation. You'll recognize this. There are 4 treatments. This was the first one we put in. Al LeBrun helped us with that. Right now, we've got 5 installations that are logged with a bunch more lined up. We do baseline measurements, including understory. We do breeding bird surveys. We take 360-degree photographs at every sample point, imagery, on. And all that serves as a baseline for future researchers to work on. There's just a few pictures from the Grand Falls MASN trial at American Forest Management. Just a variety of treatments that are out there, from overstory removal to a clear cut and a crop tree. So to finish, because it's time to take some questions, I put up this map that Jenna created yesterday. These are our research trials in Maine that are in the CFRU. But I think it would be very exciting if we were able to expand and make this really a regional study and try to get more people involved and a wider scope of our influence. So that's all I have. We can take some questions.
Great. Well, thank you, Brian. So far we have one question, and this is a question for Ivan. This is from Steve Pelletier, and regarding Bear Brook, he's wondering, are there any known vernal pools, significant or otherwise, in your research area?
We've never assessed specifically for vernal pools. I'm sure there's one, about 5% of East Bear is wetland that I think would be classified as a vernal pool, but the rest of it is pretty freely drained. Its slopes range up to like 25%. So it's not until you get below the weirs, then yes, but most of the work we've done some big carbon studies that included all the way down to Bear Pond, which is well below the weirs. But most of the work has been above the weirs, and above the weirs, not so much by way of wetlands because of the slope or vernal pools.
If anyone else has a question, feel free to type it in the chat box. In the meantime, I'll just remind you that if you have indicated that you wanted to get credit for this webinar, please check your email in the next day or two. I'll be sending out a form that you'll fill out and in order to get this credit, and I'll be following up with a certificate as well. We have a few more minutes, so we'll wait and see if anybody has any questions. Okay, so there is a question. Will this be recorded and possible to use for educational purposes? Yes, this is being recorded right now. And in a few days, I'll have this up on the public-facing CFRU website. And so yes, you can use it for educational purposes. Well, if that's all the questions we have, we can end a bit on the early side. Thank you all for coming. Thank you to Ivan and Brian for presenting for us today. And we hope you join us next time.